Okay, ions. So I mentioned earlier how you form ions. You do it by either adding to or removing electrons from a neutral atom, right? So if you add electrons, like for the halogens, you add one electron to chlorine, you get a Cl minus ion, right? So if chlorine is 17 protons, how many electrons would it have to give you that minus charge? 18 electrons, right? One extra. If we're going to form table salt, then sodium is going to be positive 1 charge. So how many electrons would it have? 10. Right? It has 1 extra proton that's not neutralized. That makes it a positive 1. And then sodium chloride forms a compound by electrostatic attraction. Sodium attracted to chlorine. Once you transfer that electron from here to here, you get ions, and then the ions attract electrostatically. That's one type of compound, ionic. Okay, let's see. So we've gone over that. Now, generally speaking, when metals and nonmetals combine, they form ionic compounds. They do it this way. And when they do that, each group has a characteristic charge. So in this case, they always form a +1 charge. First group, +1. Second group, +2. Skip these, and +3, +3, +3. Ooh, it gets wishy-washy in here. Those are definitely +3s. But the other side, these don't form ions. They don't form compounds, so they're zeros always. But these are -1, the halogens. So 0, -1, -2, -3, and then kind of indefinite. So remember those rules. Halogens, actually we should have gone over here. -1, -2, -3 when combined with a metal. Okay. When it's combined with a non-metal, that's a different story, and we'll cover that. Now you'll notice also in that periodic table that I gave you that where is it? Here it is. You'll notice that in the upper right-hand corner of each one of these cells is a list of charges. These are available charges for the element. They're not definite. They're available, right? So you'll notice that all of these alkali metals, they're always that 1 charge, never anything else. Alkaline earths, they're always the 2+ charge. The halogens vary a lot, right? But until you know different, consider them -1. Okay, oops, we're out of time. Let's see. Can we finish? We came close. Yeah, that's close enough. So Thursday we'll get chapter 5, nomenclature. How do you name these things?
Oh, that's fun. So the next thing will be on 4 or 5, and will there be any other chapters?
Nope, just those 4 or 5.
Got it. I finally got snake eggs worked out last night. We used to be in my mom for us until like Now you're trying to figure it out, emailing people. But we gotta figure it out so now I can read and take the test for the past one. Or the homework.
Okay.
So hopefully I'll get that done either today or tomorrow, and then I can work on this chapter.
I checked this morning, and everybody is in there through Blackboard.
Through Blackboard?
Yeah, you got to go through Blackboard.
Okay, I'll try. I got it to where I can go through the Centigrade website. I'll try. It might be easier through Blackboard.
Yeah, just go. Yeah, just go into Blackboard, and under Start Here, just look down, and you'll see a Cengage link. Go to that link. It may ask you to enroll again because it treats it as if it's a completely different course.
Oh, okay.
Okay. So don't do any work on the Cengage site. Do it
Through the
within Blackboard. That way the grades are automatically dumped into your grade book.
Okay, so what you can see and all that.
Yeah.
So definitely go through Blackboard then. Okay.
Yes, please.
Got it. Thank you.
You want me to take a test now?
Wherever you're comfortable. We've got this room. Nobody else is in here, so you can, rather than pack things up, you can just sit right back down.
What do you say?
Yeah. And we're recording. Yeah, let's crank this up. All right. That's okay. I just didn't want to slam more in your face. Have the known lock students out. Check the door. Okay. Chapter 5. Nomenclature, which is a fancy word for naming compounds. We don't want to just name the compound. We want to be able to write the formula for the compound based on the name. In order to do that, the conventions, the rules for naming compounds have to be such so that there's no ambiguity in the name and the compound that it associates with. You've got to be able to write the compound from the name and no other formula. Just only one way will satisfy. So we're striving for non-ambiguity. Okay. That's just an outline of the rules. Okay, we're going to begin, and the convention begins with what we call binary compounds. That is, there are two parts to the compound, and consequently two parts to the name. Sometimes it's just two elements, like sodium and chlorine together, make table salt. But sometimes you have a combination of maybe an element and a group of elements that behave as if they were one. Those are the polyatomic ions. We'll get to those in a minute. But the concept is that your name is binary. You have a part 1 and a part 2. We're going to begin with binary ionic compounds because they're the simplest. So we'll start simple and then we'll gradually complicate things. When you have an ionic compound, it's invariably a combination of a metal and a non-metal. So the metal's going to come from over here somewhere, and the non-metal, of course, over here. And that'll make your binary ionic compound. The metal is going to be what? Positive or negative charge? Positive, right? So that only leaves negative charge for the nonmetal. But we get to the point where you don't just have compounds with one from here and one from here. A whole host of compounds can be constructed from two of these, two nonmetals, but their bonding is different. A metal and a nonmetal typically create an ionic bond, where one is actually a positive and the other is a negative. But for covalent compounds, neither one is charged. They share electrons in the process of bonding. But for simplicity's sake, we use conventions that were developed earlier for the metal-nonmetal arrangements to carry over and name the covalent compounds with slight variation. And that'll become, hopefully, crystal clear once we start looking at the rules. Okay, so we mentioned that. The positive charged ion is called a cation, and the negative ion is called an anion. You just have to memorize it. Cation for positive, anion for negative. So the binary compound is a combination of cation and anion. And in writing the compound and in naming it, the cation always comes first. We do positive, then negative. That's just a convention. Okay, we're going to talk about the three types of compounds. We're going to break them into three types: type 1, type 2, type 3. And let's skip that and actually get into naming. All right, type 1 compound. We have a metal with a nonmetal, or a cation and anion. There's one more restriction. The metal may have only one possible charge. In other words, it comes from a part of the periodic table that says when this metal forms an ion, there's only one possibility. You can't have multiple possible ions. In other words, under one circumstance, you have a positive 1 charge. In another circumstance, you maybe has a positive 2, positive 3. For the type 1 compound, the metal is fixed in its charge, right? And it's easy to find out where they come from. All these guys are always +1. Alkaline metals are +1.
So type 1 is always +1.
No, they just have a single charge. These alkaline earths are always +2. Okay, +1, +2. This one, and this one are always +3. Okay, so that does it for the metals. Of course, once you know what the charge on the metal is, then you can deduce. Sometimes you can deduce the charge on the anion. But if the anion comes from here, we always give it a -1 charge. And if the anion comes from here, we give it a -2. Comes from here, we give it a -3. So working from left to right, +1, +2, +3. Working from right to left, -1, -2, -3. Okay, we'll do some examples. Let's see. First thing you do, let's just take an example. Say we have this compound where you're combining a metal and a non-metal. Right? Where does it come from? There's sodium, so it has to have a +1 charge. I'm just going to pencil that in, as they say. And chlorine always have a -1 charge. Right? So we know that compound is written correctly because neutral compounds have to balance. A +1 balances a -1. So you only need one of each. Right? Now let's name it. We wrote it that way, so we're going to name it. The cation is always just the name of the element. So we would say sodium. And then the anion, we change the ending to IDE. Okay, so that's sodium chloride. Now, can we go backwards? Could we write the compound from that name? Well, we know it has sodium in it, right? So we just write the element. And we know it has chlorine in it, so we write the element. Then you look at the charges. Chlorine has a -1 charge. Sodium always has a +1 charge because of where it comes from on the table. And then you look for balance. One of these, one of those. That's it. It's written correctly. Just one sodium, one chlorine.
Wait, so how do you know what their charges are?
Because of where they come from on the table. These are always +1. Those are always +2. These are +3.
What about the ones in the middle right there?
We'll get to those in a few minutes.
What if they have more charges? Like if it's like,
We'll do another example. Okay? How about this one? The road crews in the winter throw a lot of this on the road to melt the ice, right? But it damages concrete. It's murder on concrete. Asphalt, no big deal. But concrete, it will destroy concrete in just a few seasons. So sometimes they mix in a substantial amount of this compound. Calcium chloride. And if you go to Walmart or some other hardware store and you look at the bags, and some of them are called like Superheat or whatever, look on the bag, it may be that compound exclusively, because you can throw this out on your concrete walkway, won't damage it. Whereas this one will. Plus, this one is more effective. That's why they call it Superheat. Huh?
I don't use that.
Because it's too expensive. All you got to do for this one is just dig it out of the ground. They got mines up by the Great Lakes. They go down on land, and they go out under the lakes, and just mine it out.
I know some other states, they use something that's, I think, a liquid form. Melts the snow, but I don't know.
It depends on their equipment. Maybe they form a concentrated solution of this and just throw it out there. It'll still be fairly effective. So let's write that compound. Under type 1 rules, does it fit? Calcium, where does it come from? Calcium's from here. Always +2. Right? So we know we have calcium and we have chlorine. And calcium is always a 2+ charge. Chlorine is still -1. That didn't change. Okay. Now, you've got to have enough of each one to balance charges. So it's the simplest ratio. You just need 2 of these. Okay. So now the total charge, total negative charge, is 2 times 1 is 2 minus. balances 2 plus. Okay? It's like if we wrote like the atom, it would have, it would be, all right, let's do that. Calcium is 20, right? So we have 20 protons, but we only have 18 electrons, right? That gives it a 2 plus charge, right? So with chlorine, we have 17, but it's a 1 minus charge, so it has 18 electrons. So they both have the same number, but because of the number of protons, they have a different charge. So that gives this one a 2 plus charge. That gives this one a 1 minus charge. Right? So this one balanced one of those, but we need another one to balance the other. So you have these two negatives balancing that one 2 plus charge cation. Okay? Now let's see. Let me pick one more, and we'll go the other direction. This way, we had the name and we went to the compound. Now let's have the compound and go to the name. So let's try, okay, how about this one? I want a compound of aluminum and oxygen. Okay? First, you got to write the compound correctly. Right? So aluminum is always 3 plus, right? Plus 1, plus 2, plus 3. So I just pencil this in just so I can keep track of my charges. How about oxygen? Minus 1, minus 2. Okay? So how are we going to balance an even with an odd? We'll use a math trick. It's called cross multiply. Did you say it? Cross multiply. Yeah. We just move this 2 over here and that 3 over here. And then check yourself to be sure, right? So 2 times 3 plus means you have a total of 6 plus for the cations, right? Because you have 2 of them. Each one is 3 plus. How about this one? You have 3, 2 minuses. So that's 6 minuses. And you have 3 oxygens. Each one is 2 minus. That makes a total of 6 minus. So now we're balanced. So that just proves that the cross multiplying works. All right, so now we have the compound is written correctly. And when you write the compound, you don't have to put the charge in it. I just do that so it's easier to budget my charges. But this is the correct way to write the compound. Now let's name it. We have aluminum. On this side of the pond, it's aluminum. The other side of the pond is aluminium. The British have always been weird, so we let them get away with it. And then oxygen. Instead of saying oxygen or something that doesn't sound right, we just say oxide. This thing's not behaving. Okay. Now, does this satisfy the type 1 rules? We got a metal and a non-metal, cation, anion, that's true. Does the metal have only one possible charge? Yep. Plus 1, plus 2, plus 3. Always. So we're safe in using this convention. We just have to say aluminum oxide. And it's unambiguous. It's not redundant. We know aluminum has a 3 plus charge always. We know oxygen always has a 2 minus charge. So when you combine them, they can only occur in that ratio, right? So we can go backwards and forwards with no mistakes.
So which ones are negative, like in the rows?
Oxide. Oh, over here, -1, -2, -3.
So what about 18 and 14?
About what?
Like the rows 18 and 14.
Oh, this one and that one, these never form charges. They're noble gases. And these are kind of squirrely. See, they're close to this dividing line. Sometimes they go one way and sometimes they go the other. Now you can form ionic compounds with carbon. We call them carbides.
Where do they go?
I'm sorry?
So what's their charge?
In that case, when they're in the carbide form with a metal, they're a negative charge. And they can be a -2 or a -4. So that's why I didn't hammer on that one, because it's a little squirrely. And at this point in the learning curve, we don't want to introduce any weird, right? We want to keep it simple. So if you stay with -1, -2, -3, +3, +2, +1, you're good with type 1 compounds. Okay?
You said +3, I understand the column 1, 2, 1 and 2 charges. +3 is 13, you said?
This one, yes.
Yeah, okay.
And you're right to notice that we skipped over these entirely. We just went from here to here to here. And later on, hopefully, you'll understand why that is.
So when we look
But
at,
right now, just memorize it.
when we look at column 1, when we see hydrogen, we always kind of need to think it's off on its own, really don't matter.
Yeah, hydrogen is special. But it usually, when hydrogen forms an ion, most of the time it loses an electron and makes that. So if you look at it, it only has one proton, right? One electron. So if it loses an electron, that means it has an extra proton, but it only has one proton. So an H+ ion is identical to a proton. That always twisted my head around too. But it's true. But hydrogen can, in some cases, take on another electron and become a minus charge. And that's why I left it out of the type 1 compound rule, because it is special. These guys behave. +1, +2. Now, type 2 compounds. Okay, we still have a metal and a non-metal. Right? Cation, anion, I'm not going to write that in again. Only in this case, type 2 compounds, the metal may have 2 or more possible charges. That doesn't mean it has 2 different charges in the same compound. If it's in a compound, it has one charge, but it's not fixed. In other words, it could be one charge in one circumstance, one compound, but in a different compound, it might have a different charge, right? So in those cases, we identify the charge with a Roman numeral. Okay? For example, and for simplicity's sake, those metals come out of this slice right here. And then some of these too. But the transition metals could have more than one possible charge. There are exceptions, and I'll get to those. But for the most part, these guys in here and here, they could have more than one possible charge. So they fit into the type 2 scenario. We're still combining them with an anion, and the anions are fixed, usually fixed in their charge. So we don't have to worry about those. So let's say we have, oh, I've been accidentally punching buttons down there. Let's type 1s, okay. Let's see. Type 2s. More than one possible positive charge. And in that case, we have to specify what the charge is in the name. Okay, so let's do an example. Let's say we have this one. Fe2O3. It's the principal compound in iron ore. So when the smelters get hold of the iron ore, they've got to extract that iron from this compound. So, what do we know? Well, we know we have iron, right? So that doesn't change. Iron's the cation. And then oxide is the anion. But notice I left a space. That's where I'm going to put the Roman numeral to tell me what charge is on that iron. Okay, so in parentheses, we have to figure out what the charge is on the iron. So remember, all compounds are neutral. That is, the charges have to balance. So the oxygen from here is what charge? 2 minus. So I just pencil that in so I can start my budget. And if we have 3 oxygens at 2 minus each, how many total minuses do we have? 6 minuses, right? 3 times 2. So that means the total over here has to be 6 plus to balance that. Right? If the total over here is 6 minus, the total over here has to be 6 plus. So we're going to divide that 6 plus among the irons. So if we got 2 irons, how much is each one? 3 plus, right? So each one of these is 3 plus. So we put a Roman numeral 3. That tells us the charge on the iron. Yes, always in parentheses. Let's see if we can do, well, we've probably got examples up here. Why don't I let slideshow do some of the work? There's some possibilities. So iron, we worked with this one right here, iron 3 plus. An older system, you should feel lucky that you don't have to learn the older system. Like I had to. The newer system is much easier, more straightforward. We just say iron 3 oxide. In the past, I would have to say ferric oxide. And whoever saw that name would just have to know what ferric means. Ferric means 3 plus. But you don't have to do that. What if we have, let's work the other direction. Say we have, let's say we have copper 2 fluoride. No. And switch again. copper to fluoride. Okay? Now let's write the compound from that name. Right, we know we have copper, okay? Cuprum, and fluoride, which is just F. Okay? Now we need the subscripts so that we can be sure the charges are balanced. So what's the charge on fluorine in this compound? 2 minus 1, right? 0 minus 1. It's a halogen. Okay. How about copper? Well, we're told what the charge is on copper, right? Because it could be more than one charge, so we have to be told. So this is 2 plus. Right, so how do we get the charges to balance? Well, this one only has 1, so we need 2 of them. So 2 times minus 1 is minus 2, balances a 2 plus. Okay? It's unambiguous, can't make mistakes if you follow the rules. Go from here to here. We could go backwards just as easily, like we did for this one. You should be able to go both directions. There we go, we're back in business. Exam 2, Chapter 5, Nomenclature on September 5th, Part 2. Okay, so I'll just go back through this again. When a compound is followed by a parentheses with a letter in it, there are a whole host of different letters that can be used. But the only ones that are really important for us and for most chemists are these 4. It's either G for a gas. I'll use examples. Those 2 examples there. This one was the one we were talking about in the interim. Hydrogen chloride, gas. Water, liquid. Dihydrogen oxide. Solid, this is silver, solid. And then aqueous, if we take that gas and dissolve it in water, we get an aqueous solution of hydrogen chloride. And then we use the acid naming convention that we'll get to before the end of this lecture. Okay. So let's see, we have some examples here. Copper 1 bromide. If you have this name, you can write that compound because bromide is a halogen. So it only has a minus 1 charge. Right? Copper, we're told what the charge is on copper, right? So it's plus 1. So you only need 1 copper, 1 bromine. They neutralize each other. Plus 1, minus 1. We're done. Just need 1 of each. That's why this is unambiguous and the simplest whole number multiples for each one. That brings up a good point. Technically speaking, if you write 2 here and 2 here, that would be neutral, right? Right. 2 minuses and 2 pluses. But also by convention, you want the simplest whole number ratio. Right. So 2 and 2 can be divided by 2 to equal 1 and 1. So this is the correct way to write it. Right. For something like that, that is the simplest. Right? You could write 4 and 6, and it would neutralize the charges, but it wouldn't be the correct way to write it. You want the simplest whole number ratio.
So you did have 4 and 6, which you made 2 and 3.
Yes.
Okay. So you always simplify basically.
Yeah, if you can divide through by, usually by 2 or divide through by 3, then that tells you that you can simplify. It's like reducing a fraction. Okay, let's see if we have any others that are particularly interesting. There's a sulfide, iron 2 sulfide. So it comes from the chalcogens. Minus 2, minus 2, minus 2. And iron is, we're told iron is 2 plus. Now, if you had this compound, you could write the name, because we know this is always 2 minus because of where it comes from in the chart. So that means once you have this compound, if that's given to you, then you can't change any of these ratios. You have to determine what the charge is on iron by what you're given. Right? So this would have to be 2 plus to balance that one. That's why iron 2 sulfide is the correct name. Okay. Lead 4 oxide, similar situation. Oxygen is a minus 2. So 2 of them would be minus 4 total. So that means lead has to be a plus 4 to balance those two minuses. It's like making your list for the store. You need 2 gallons of milk, right? So you put 2x milk, right? That's the way I do mine. So if each milk is a 2 minus charge, you have a total of 4 minus milk charges. Okay. All right, let's do this one. Name of the compound, CrO2. All right. If you're given that, you just have to assume that's correct, right? And work from that to name it. So what's Cr? Chromium, right? Chromium. I used to have a banana seat high handlebar bicycle, and the frame was chrome plated. It was flashy. We used to chrome plate bumpers too, right? On cars, they weren't plastic. You had this huge, heavy, thick steel bumper on the front and the back. And you want to keep it from rusting, of course. So somebody came up with a bright idea. Well, let's just plate it in chrome. That'll look flashy and nice, silvery color. It's a heavy metal, so when you bump into somebody else, it'll resist the impact. There were no shock absorbers. When you hit somebody with one of those bumpers, that shock went through the entire frame. So if you hit them hard enough, it'll bend your frame, right? So shock absorbers is probably a better idea. But if you go to some of these antique car shows, I think they have them over there by Staples sometimes in that parking lot. And maybe down where I'm from in Crab Orchard, the Baptist Church has them in their parking lot sometimes, right there on the 4-lane. You'll see some of these antique cars, and they'll have chrome-plated bumpers. Okay, so that's chromium. And then oxygen is oxide, right? Now, I didn't leave myself my drink there. Open it up. Because where does chromium come from? Transition metal. So it's going to be a type 2 compound. Right? It's not from a region or from a group that has one fixed charge. So chromium could have more than one charge. Oxide, of course, is 2 minus. So that means a total of 4 minus, right? Right, so we have to balance that. And we only have one chromium to work with because we're given this formula and we can't change it. So with one chromium, we have to balance that 4 minus charge, which means that chromium is 4 plus. Right, so that's the name of the compound, chromium 4 oxide. how we doing on time? I better not spend time on this one. I'll let you look at it. They're probably homework problems. Oh, maybe we better. Yeah. This has a critical thinking component. So let's do it. So, what's the correct name for a compound that results from the most stable ion of sulfur? And the metal that contains 24 electrons. So this metal has 24 electrons. And that's that X like I used before. There's nothing with an X up there, so I use the metal, the X, as a space filler. Okay, so what's the charge on sulfur? Well, we look, where does sulfur come from? Right. So the most stable ion in that one is 2 minus. Right. So 2 minus here, like that. And then that means this one. And here's the problem with that question. It doesn't tell you how many of those metals there are. So you have to assume that there's only one of them. Right? That's my beef with this slide. So if we assume that there's only one of them, then this one also has to be a 2 plus charge to balance that 2 minus. Right? So we're told it has 24 electrons. How many protons does it have? If it's in excess of 2 plus, it has 26 protons, right? Because 24 of them are balanced, and that gives you 2 extras for the charge. Now that we know how many protons we have, we just look at the chart, follow it till you find 26, because it's iron. So we have iron. Actually, iron 2 sulfide. Okay. I don't know what we'd do if we said, okay, maybe we should say, what if there were 2 sulfurs? Then that would change the whole mix. But if you assume it's 1 to 1, that's the answer. And if you're sitting there and you come upon a question like that, a test, you're within your rights to ask me, how many metals are there? Right? And I'll tell you. Okie doke. Now we need to get on to type 3. No, yeah, type 3. Type 3 compounds. We're still talking about binary compounds, but in type 3 we have a non-metal and a non-metal. Okay. With a non-metal and a non-metal, you don't know what the charge is. Not really, because there is no charge. 2 nonmetals do not form ionic compounds. They form covalent compounds, right? But we're going to take advantage of the convention up to this point and just modify it a little bit. So whatever the formula is, we just name it first as if it were a cation. Okay. So if we have something like this one, you're given that formula, so you have 1 carbon and 2 oxygens together. Right? So carbon comes first, so we just write the name. And oxygen comes second. But since we don't know what the charge is on carbon, and oxide is all we get out of the second one, right? But if we just say carbon oxide, that is ambiguous because it doesn't say how many there's no way we can determine how many oxygens there are from that formula, from that name. Because there are no charges to deal with. So the convention in type 3 is you say how many there are. And you use the Greek prefixes, right? For, I have to go back over here and erase type 1. The Greek prefixes, and they should be in your book. So the Greek prefixes for 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going to stop at 10. They go on and on and on and on, but 10's enough for us. This is mono. This is di. This is tri. This is tetra. This is penta. This is hexa. This is hepta. This is octa. This is nona. This is deca. So those are the Greek prefixes that mean, if it's in front of an element, this means that's how many there are, right? So in this case, we've got 2. So we insert in front of oxide a di. Okay. Now, that tells us, first of all, you look at the compound and say, what do we have? Carbon, oxygen. Carbon, oxygen, both nonmetals. So you instantly know it's type 3 naming convention. Right? So that means you have to say how many there are. So you write the carbon and the oxide and how many there are. When there's only 1 in this first position, you don't say mono. You leave the mono off. If you've got one of them there, you have at least 1, so you don't, mono is redundant. Now, of course, in the second position, we do say mono. Like this one. That's supposedly the global warming compound, right? But everybody who studies the data knows that it's not. It's not significant. I say it has potential to be global warming, but there's not enough of it to make a difference. Now, go to Venus. Oh yeah, there's plenty there. I mean, that's definitely a contributor to warming on a global scale for Venus, but not for us. Because what do we have? Like 380 parts per million. Some places maybe up to 400 parts per million. That's not enough. Anyway, but this one, that's the poisonous one, right? You take a tube from your tailpipe and run it into your car, duct tape it off into the cabin, then you get in there and start the engine and, look while you're going because of that. This one is carbon monoxide. And just for aesthetic purposes, we don't have 2 O's here, monooxide. We drop one of the O's. It flows better, monoxide. Okay, let's see, they'll probably give us some other examples. Well, there you go. They only go up through 8. I went up through 10. Example, carbon dioxide. Okay, there's sulfur and fluorine. Right, sulfur, hexafluoride. Hexa for 6 fluorines. Okay, let's see, that gives, oh, here's a good one. Nitrogen and oxygen together, right? We look, check, be sure. Yeah, they're both nonmetals, type 3 convention. Now we have 2 nitrogens, dinitrogen, tetroxide. We drop the A. Instead of tetroxide, it's tetroxide. Okay, so that's something more for you to memorize. The prefixes. There's another one. How about, let's go back the other direction. Let's say, do this one. Dinitrogen monoxide. Okay. We have nitrogen. How many of you? 2. And then oxygen. Just 1. That's also known as a, this is the IUPAC naming convention. International Union of Pure and Applied Chemists. They dictate how to name compounds, among other things. So this is the IUPAC name. So when I say IUPAC name, that's what I mean. Now there are trivial names, you know, just like H2O is water. The trivial names, well, actually that's a bad example because IUPAC recognizes water as a standard name. Let's try it, that's a different one. This one, N2O, dinitrogen monoxide, we used to know, still do know, as nitrous oxide, laughing gas. Okay, so if your dentist likes to use the stuff, you'll have a tank somewhere, maybe have it piped into the room with a mask, or you might have a tank sitting in the corner. I don't know. I've never actually used nitrous oxide in the dentist chair. Some people have, they say it's loads of fun. But that's a trivial name, nitrous oxide. This is the IUPAC name. What's the name of this compound? All right, so now we have to decide which convention to use for SeO2. Okay? And where do they come from first? First of all, selenium, right? The nonmetal, right? Oxygen's a nonmetal, so we type 3 convention. Right? So you just say selenium dioxide. Okay. Some people like flow charts. You know, if you want, start with a binary compound that is 2 components. Is there a metal? Well, if there's a metal, it's either a type 1 or a type 2. Right? Decision-making process. If there are 2 metals, then you go down this route. I mean, if there's a metal, you go down this route. If they're both non-metals, you go straight to type 3 and use prefixes. If there's a metal in there, you have to ask yourself, is the metal a fixed charge or is it variable? If it's fixed charge, then it'll come from here, here, or here. Okay? Then it's a type 2 convention. If it's not a fixed charge, that means it comes from here, here. Then, did I say type 2? Type 1. Type 2 is this one. Type 1 is the earlier one. Type 1, fixed charge. Type 2, variable charge. Now, there are some exceptions. Silver is always +1, never anything else. So technically, you could use type 1 for silver. Right? So if we have a compound that's silver chloride, which happens to be a solid, then we could say silver chloride. And that would be it. But I'm going to allow, for simplicity's sake, if it comes from here, you can say what the charge is, and I'll count it right. So you can say silver 1 chloride, and I'll accept it. Because silver comes with transition metals, and to minimize the number of rules you have to, exceptions that you have to memorize, you can say silver 1 chloride, or silver chloride, either one works. There's one other one here, I'm trying to think which one is it. Not copper. I think it's
So if
zinc.
it's a 1, we don't have to put in parentheses usually. So if you're-
For silver,
For any of them.
no, only for silver. The rest of them, except for the one I'm searching for now, have multiple charges. I'm just saying that's an exception. Where's my, here it is. Yeah, I was on good. Zinc is another one. Zinc is always 2 plus. So if we say that, then you could say zinc chloride. And that's unambiguous. But since it's a transition metal, you could also say zinc 2 chloride, and I'll accept it. Okay, that takes care of the naming conventions, I think. Now we'll go to polyatomic ions. All right, what is a polyatomic ion? Well, first of all, it's an ion. It has a charge, right? But in that group that has a charge, more than one atom. And there are always at least 2 different elements, sometimes 3. So that's why I gave you that chart. I think I gave you a copy of that chart. There you go. There it is. Actually, it's part of your 50 ways to name your compound. The extra credit. Let me show you. This one, that extra credit thing, the last page is a list of polyatomic ions. Okay. These are the ones that we're going to be concerned with. And you'll see that there are several atoms together in that group, and they behave as a single unit. And they each have a special name. So you don't have to do any name conversions like we did with chlorine to chloride. It's just the name means that ion, and it has a specific charge. Okay? So why should we be concerned with polyatomics? Because in the compounds, they behave as single units. In other words, if it's a binary compound, you might have an element as your cation and a polyatomic as your anion. It's still a binary compound because that polyatomic behaves as a single unit. Let's see. These are examples. That's not all of them in that list. Notice also the list is not, these are not unique all the way across. This is the list here, sorted by name, alphabetical order. This is the list sorted by formula. Right? So it's one list sorted 2 different ways. Okay. Plus at the bottom you've got your prefixes for your Greek prefixes for numbers. So whichever one you prefer to use to find the polyatomic. This is a short list. And first thing you'll note is that in this list and in that one, there's only one polyatomic that has a plus charge. That's ammonia. Behaves as a unit. All the rest of them are negative charges. Either a -1 or a 2 minus. There's a 3 minus. I don't think they go any higher than that. Yeah. -1, -2, -3 is the highest one. And this one has a special name. Ammonium. Now, where would that go in the name of a compound? First, right? Yeah, because it's a cation. It would never come second. Whereas the rest of them are all anions. They always come second in the name. Okay? So if we formed a compound with this polyatomic and say, let's keep it simple, chlorine. Right? That's a +1, that's a -1, it's balanced. One of these groups, one of those anions, ammonium, chloride. Now, which one is that? Well, since it's a plus and a minus, it would either be a type 1 or a type 2 convention. It has to be a type 1 because it's a fixed charge. All the polyatomics are fixed charges. So if you have this in there, you would consider it a type 1 and just say ammonium chloride. You wouldn't have to say the charge. Because when you say ammonium, it's always that. Okay? What if we combine ammonium with another polyatomic? You can do that. How about, let's pick one. How about this one? OH minus. That group is a -1 charge, ammonium. Hydroxide. We don't have to change the names in any way because with polyatomics, the name is fixed, just like the charge. So there's hydroxide and there's ammonium. That's our compound. Now, what if you have a compound with a polyatomic that's combined with, let's combine it with another polyatomic. How about this one? SO4 2 minus. Now, how are you going to balance the charge? That polyatomic has a +1. This polyatomic has a 2 minus. So you need 2 of these, don't you? Right? Well, you don't put a 2 down here and an 8 down there. You have to put a parentheses around it. You need 2 of those polyatomics. Why? Because a polyatomic is a single unit. If you change the subscripts here, you've changed the group. It's not the same anymore. Right? So in this case, we would have there, 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 and there. That's our polyatomic. And that polyatomic has a +1 charge. Okay? Now, why do they behave as single units? Why don't they just break up? They make individual, when they react with something, form individual nitrogen and hydrogens. Because the bond that hold them together are much stronger than the ionic bond that forms the union. Right? These are covalent bonds. They're much, much stronger than ionic bonds. So they behave as a unit. Now, there are, to help you understand and memorize the polyatomics a little easier, there are groups in there that form a pattern, right? That's why I outlined this one. That's a good place to start. In this polyatomic family, you might call it, you've got chlorine and oxygen combined in various ratios, right? One chlorine and different numbers of oxygens, right? And each one of them has a different name. Right? So let's simplify it. I start with the one, in this case, chlorate, right? So we have 3 of these with a -1 charge. Now, if I take away an oxygen, it's still got a -1 charge, right? But it's got a different name. Change the ending from 8 to 8. Right? Take away 1, got an 8. We can take away another one, but we don't have any more endings. So we have to put a prefix in here. We're going to say underneath or less than chloride. It's like hypodermic needles, or hypo is underneath the skin, dermis is underneath chloride. So it's 1 less than chloride, hypochlorite. And you can go 1 more the other direction. But we need a prefix for this one too. So this one is prefixed on that one because it's just above it. Perchlorate. I'm not exactly sure what per means. If we use an analogy here, if this is less than chloride, this is more than chloride. We can look it up later. I should do that so I'll know. But that's a family of chlorine and oxygen together in a polyatomic. Now, notice this is a halogen. You can substitute another halogen in here, except for that one. Fluorine doesn't behave like the rest of them. But you can put a bromine in there, right? So if we put a bromine in this one, that would be what? Per bromate. And if you did the same substitution down here, you'd have bromate, bromide, hypobromite. So by using that convention, we can build 4, 8, 12 polyatomic ions just like that. Iodate, iodide, hypoiodide. Okay, so that works with these 3. Let's see, where'd that go? Yeah, there we go. And if you look on the right-hand side, you'll see the grouping such that here is the grouping for the chlorines. Here's the grouping for the bromines. And there should be one for the iodide. Iodide's not there. Okay. So if I give you a question that has iodine in it and it's not here, just ask me. Now there are others that don't follow the convention quite as closely. That eliminates 12 possible ones that you have to memorize. You just know the convention, and you can build your polyatomic. You don't even need that. Now, when you're looking at a compound, for instance, this one. This is a -1. How do you know if you're trying to write this compound? We're not finished with it yet. If you're trying to write this compound, how do you know that you have a polyatomic involved? Well, one clue is you've got 3 elements in there, one of them's oxygen. That's a clue. It's not a dead ringer, it's just a clue that you should suspect polyatomic. So if we suspect, and we look it up in our table, because this will be on the exam, right? You don't have to memorize that. It'll be in useful information. Then we know that that's -1 charge. Right? So we know that magnesium, because it comes from here, has a 2+ charge. So that's a type 1 compound. So with a 2+ here, how do we get those to balance? Right? We can't bust up the polyatomics, so we have to use parentheses. Like that. Okay? And that's the way you would write magnesium chlorate.
They're always grouping the last two together.
Mm-hmm.
They're always grouping the last two together.
Well, this is unambiguous. I can write that compound from this because I know what chlorate is. Right? I know what magnesium is. I know what the chlorate charge is. It's fixed. I know what the magnesium charge is. It's fixed. Then all I have to do is balance the charges. 2+ against 1- means I need 2 of these. But we don't change the subscripts of a polyatomic. That's the easiest way to crash and burn. Use parentheses. All right. So there's another example of a polyatomic with a polyatomic. This one, C2H3O2, is a common compound. Anytime you make a salad dressing, you use that. It's vinegar. Well, this is acetate ion, but if instead of ammonia, you put hydrogen there, then you've got acetic acid. 5% solution is vinegar. But in this case, we're only using the acetate ion. Right, there it is. Combined with ammonium, a -1 + 1, you only need 1 of each. So that's ammonium acetate. Okay. I need to get through this to acids. Sorry, I'm going to have to rush through this. Naming acids. Okay. First of all, how do you recognize an acid? If you're given a compound, an acid will always have that as the first element in the compound. There may be more than 1 of them. There could be 2, there could be 3, right? But this will always be the first one, even if the rest of it has some other hydrogens in it. The reason they write it that way is if there are extra hydrogens over here, those hydrogens do not contribute to the acidity. So what do I mean by that? Well, say we have, like our earlier compound, HCl. If you put it in water, what's it going to do? It's going to react with the water, and this hydrogen is going to break away from the chlorine and become protons in solution. That's where you get the acidity, from the protons. So that's why we write them first. These are protons available for dissociation to make the acidic solution. Okay. When you have, everybody know about pH meters, okay, or even litmus paper or pH papers. They're keyed on that one right there. Right. pH meter has a probe. Used to be on glass, now they're plastic, so they're safer to use. Mostly plastic. You always have the sensing element in there is always glass, but it's surrounded by plastic, so it's harder to break. Anyway, that sensing element is keyed upon. It responds to this concentration. So this concentration goes up in solution, you get a more acidic solution. And I know we haven't talked about how to calculate pH, but as the pH goes down, the acidity goes up. So a pH of 1 is stronger acid than a pH 2. Anyway, recognize an acid by preceding hydrogen. They always have that, at least one. Okay. All right, first thing you look for. Does the compound have oxygen? If it has oxygen, let's say, take an example. Sulfuric acid. Why did I name it that way? If it has oxygen, for the name, do not say hydro. So I'm going to put the second rule up here. Does the compound have oxygen? If yes, if it does have oxygen, you don't say hydro. If it does not have oxygen, no oxygen. Start with hydro in the name. Okay? So whereas this one, and you change, if the name is an 8, in this case it's sulfate, you change that to ic with a slight variation, sulfuric. And then you just add acid on the end. This one doesn't have oxygen in it, so we start the name with hydro. So hydro, and then you say, what is this? Well, it would be hydrogen chloride if it were a gas, right? Put it in solution, then you take the chloride and you say ic, chloric, hydrochloric. So whenever you say hydro, you know that the compound does not have oxygen. If there's no hydro, you know the acid does have oxygen. Cyanide ion, if it's HCN for hydrocyanic, CN is the cyanide ion, I becomes ic. Hydrosulfuric acid, this is sulfuric acid because it has oxygen, but that one has no oxygen in it. So it's hydro. Hydrogen, dihydrogen sulfide is hydrosulfuric. I becomes ic. Other examples. Acids with no oxygen. Notice they're all hydros. Start with hydro. Then, of course, if you have oxygen in the name, of course, you don't start with hydro. Examples: HNO3, elements. One of them is oxygen, suspect a polyatomic, and it is. NO3 is nitrate. So when you convert this, of course, you don't say hydro, but nitrate then becomes nitric. Eights become X. How about this one? NO2. If you look in your chart, you'll find that NO2 is not nitrate, it's actually nitrite. Remember when we took away an oxygen, we went 8 to 8. So this is nitrite. Now, in this case, ites become us's. And ites become us. So 8 ic, ite us. Nitrous acid. How about, let's go one further. How about this one? HClO. Right? Remember we had ClO3 was chlorate, and then ClO2 was chlorite, and then ClO was hypochlorite. So in that case, we've got oxygen, so we don't say hydro. This is the hypochlorite polyatomic. So we say hypochlorous acid. Okay. Ite still becomes us, but we don't throw away the hypo. Let's see. There's your acetic acid. One hydrogen here, and the acetate ion. Since there's oxygen, we don't say hydro. It's acetate, 8 becomes ic, acetic acid. This is the only hydrogen that dissociates. These hydrogens are part of the polyatomic ion. Remember what I said about polyatomics? They're covalently bound. So those hydrogens are stuck hard in that polyatomic, the acetate polyatomic. They do not dissociate. Only that one hydrogen dissociates. That's why it's written out there separately. That's the acidic proton, we say. This one has 2 acidic protons right here. And this one has 3 acidic protons. This is, PO4 is the phosphate ion, so 8 become X. Only we have to modify it just a little bit. Kind of like sulfur, sulfuric. This is phosphoric acid. They put a little bit of that in your pot to keep it acidic, because an acid solution will hold more carbonation in solution. They put a little phosphoric. That's why, you ever seen the time-lapse video of Coca-Cola, and you drop a nail in it? In a few days, it's gone. The phosphoric acid reacts with the iron, produces iron phosphate. Right? It's not the acidity that does it, it's the phosphate that does it. Now, granted, Coca-Cola is very acidic. Right? Check the pH. It's down around 1.5. But so is your stomach acid. Okay, let's see. Okay, we mentioned that before. The ites become us's. There's another one, there's another one. Examples. And your decision tree. First question you ask, Well, the first question you ask, is it an acid? Right? Right? So you look for this first proton, 1, 2, or 3 of them. Right? That's the first thing that comes in a compound to make an acid. Then, if it's an acid, then you say, is there oxygen there?
Hold on, you said 1, 2, and 3, it's not gonna have more than 3.
Yeah, those are exotic acids. We're not going to deal with them. The most we're going to see is 3. Then you say, if it has oxygen in it, yes, okay, then you do not start the name with hydro. If it does not have oxygen, you start with hydro. If it does have oxygen, you don't start with hydro. Practice, practice, practice. It'll become second nature. Then you look at the polyatomic ion, or the anion. Well, it doesn't have to be polyatomic, just a lot of them are. You look at the anion, and well, actually, if the anion has no oxygen in it, it's going to be over here anyway, and the ending is ic, like chloric, hydrochloric, hydrobromic. Actually, hydrosulfuric. Right? But if it has oxygen in it, then you look at the ending of the polyatomic ion. If it's ite, it becomes us. If it's ate, it becomes ic. And then you have the other variations, like when you precede it with like a hypo, you have to keep that. The one we didn't do was this one. Right, remember that polyatomic? Per chlorate. Ate becomes ic, but you keep the per. So this would be per, since it's oxygen, no hydro, per chloric acid. Right? That's a dangerous acid, especially if it comes into contact with organic matter. We used to use this to digest organic matter to leave the ash behind. It's called wet ashing. Dry ashing is where you just heat it up and burn it off. We used wet ashing, and it would destroy the organic matter, and it would be blown off as CO2 and water and leave the ash behind, which is primarily metals. But we couldn't put it on there directly and start heating it. If you did, have a chance of explosion, violent reaction. So we would take our plant material in these tall Berzelius beakers and pour nitric acid on it, which wasn't quite as hazardous, and just let it sit cold overnight, and it would do a pre-digestion. Then we come in and add the perchloric on top of that, heat it up, and it's perfectly safe that way. And it would destroy all the organic matter and leave the ash behind. Then we dissolve the acid in hydrochloric acid and take it into our spectrometer to find out what the metals were. But the surest way, if you really want an explosion, just take a big chunk of butter in one of those beakers and cover it in perchloric acid, set it on your hot plate, turn the hot plate on high, pull the sash down and evacuate the building. Because it will blow. Okay. Oh, we're out of time. Let's see. I think we pretty much got to the end. Oh, that's 4. Oh, here's. I want to see if there's any. No, we're good. So, I gave you the review document for this one, didn't I? Yeah, that's a good source for preparing for the exam, because I build it in the same format as an exam. So you can take it as if it were a test. And then find out which ones you're weak on, go back and work on those, because the ones you get right, you don't even waste time on those. And in addition to your homework, the review document, your homework should prepare you fairly well for exam.
Is that gonna be Tuesday or Wednesday or Thursday?
Yeah, Tuesday is a review.
Thank goodness, I would love a review.
So usually what I do is I take the review document and run through some of those problems, right? And if you've gone through the review document yourself, you're invited to first say, all right, I'm having trouble with this one, and we'll get to everybody's problems first before I start yammering about something else.
I'll probably have plenty of questions and all that by then.
Good.
So I'm very happy to have a buffer day to do that.
Oh, yeah. And then Thursday we'll have our exam.
Hopefully by then I'll be ready.
Okay, let's stop this recording.